Chapter 8, Two-Body Central Force Problems, Part 2, Orbits. In the last lecture, we derived the equations of motion for central force problems. In this lecture, we will look specifically at the orbits when the central force has a inverse square law form. So in other words, when the force between the objects is inversely proportional to the distance squared. At the end of the last lecture, I claimed that the orbital paths are circle, ellipses, parabolas, or hyperbolas. In other words, the conic sections. And so we'll show that that's true in this lecture. Okay, so we're going to start with our radial equation of motion. We're going to use the version of the radial equation where we explicitly see the centrifugal force. So remember that du dr, negative du dr is just the force. So we'll replace this term with the force, and then we get the centrifugal force. In order to solve this equation, it's going to be a lot easier if we do a substitution. So we're going to define a variable u as 1 over the radial coordinate r. And so we're going to try to write everything in terms of these u variables. The second thing that we want to do is, instead of having a time derivative here, instead of r double dot, we want to write our derivatives in terms of the phi generalized coordinate. So the thing that we're trying to get to is an equation that relates u to phi, and then at the very end we'll replace the u's with r's, and so what we're going to be going for is r as a function of phi. That will tell us the shape of the orbit. Okay, so let's take on the chain rule thing first. So we can write a time derivative like this. D by dt is the same as d by d phi times d phi dt. The d phi's cancel. D phi dt is just phi dot. Now remember, angular momentum is mu r squared phi dot. So this phi dot we can write as L divided by mu r squared. And we're now going to replace the r squared with a 1 over mu. So if mu is 1 over r, then r is 1 over mu. So that 1 over r squared just becomes a u squared here. So our time derivative, d by dt, can be replaced by a d by d phi times this coefficient L u squared over mu. When you're writing this by hand, don't confuse your u with your mu. Make sure the mu's are written clearly so you don't confuse them. Okay, so we're going to use the result on the last page to write r dot as dr dt. The derivative becomes all this, which is just this right here. We're going to replace the r here with a 1 over mu, and when we take the derivative of 1 over u, we get a negative 1 over u squared. The 1 over u squared is going to cancel this u squared right here, so that goes away, and we pick up a negative sign. So r dot becomes negative angular momentum over reduced mass times du d phi. Similarly, we can evaluate r double dot. So we do exactly the same thing over again. We now pick up a u squared when we evaluate the derivative. And so you get this expression right here. I encourage you to go through this step by step and convince yourself that this is true. We can plug this thing in for r double dot. So we have mu r double dot. We have mu This thing here is our double dot with a negative sign, equals the force plus L squared over mu r cubed. We have an r cubed here, so we want to replace the r cubed with a 1 over mu cubed. Sorry, with a 1 over u cubed. And then when we simplify, and then we're going to cross multiply this thing to kind of get everything over on the other side. So I don't take my word for it. Please go through all the steps on your own to convince yourself. But you can go from here down to here. And so you get a second derivative of u with respect to phi equals u minus all the stuff times the force as a function of u. We're going to use this previous equation now by plugging in specifically for an inverse square law. So we'll do it general for now. We'll write that the force is minus some constant gamma over r squared. That gamma would be g mu m for the gravitational force, or k q1 q2 for the electrostatic force. So we're going from our equation that we had on the previous page. We're plugging in for the force minus gamma over r squared right here. Notice that when we plug in r squared, we're going to get a 1 over u squared. So, no, it's right here. So the force is going to be minus gamma u squared. When we plug this in for the force, this u squared cancels that u squared in the bottom. So this term here just becomes mu gamma over L squared. There are no u terms here. And in fact, this is why, right here, this is why we did the substitution, so that this is just a constant term. We're going to do yet another substitution. So we're going to define the variable w is equal to u minus gamma mu over L squared, or in other words, u is equal to w plus that term. The reason for doing this is that we get a very simple equation. The thing on the right-hand side is just w. And the thing on the left-hand side is the second derivative of w with respect to phi. This is an equation, you probably know the answer to it. If you take the second derivative of something and you get the negative of the something back, that's just the property of complex exponentials or sines and cosines. So we'll write the solution in this form, that w is some constant a in amplitude times cosine of phi minus delta. Delta is some phase factor. So we're going to take this as the solution right here. Solve for u, so you get that, and then factor this out. So we're going to introduce a new parameter, epsilon. And so epsilon we're defining as a L squared over gamma mu. And the reason for doing that is that it lets us just factor out this term and you get a simpler term here. It turns out epsilon actually has physical meaning also. So we'll come back to what this epsilon value is in a bit. Well, it turns out it's the eccentricity of the orbit, but we'll show this a little bit later. So here's our result. Our result is that u, which is 1 over r, equals this thing, and it depends only on phi and other constants. So this is actually what we wanted. We have u in terms of phi. If we replace u with 1 over r here, and then solve for r, we'll get some constant times 1 over this thing. And that's what we see on the next page. So again, I highly recommend that you go through all the math by yourself to follow all the steps. But you can show that the radial coordinate is a constant over 1 plus epsilon cosine phi. If you compare it to the previous equation, you can show that that constant is the angular momentum squared over gamma mu. If for gravity, it turns out that c is L squared over g m1 m2 times mu. Epsilon is that, and again, it turns out that's the eccentricity of the conic section. So it turns out that this is actually a general equation for any conic section, hyperbola, parabola, ellipse, or circle. All of them can be described by this equation with different values of the eccentricity E. So basically, we have shown that you get a conic section as a result of an inverse square law of force. One can also show that the total energy of the system is this. We'll come back to this later. Okay, so here are these conic sections. Here's our equation for the conic section. When the eccentricity parameter E is 0, this term is 0, and you just get R as a constant. So that's a circle. Turns out that the energy, which also there's a different form which we'll derive later on. It looks like this. Anyway, when the eccentricity is 0, the energy is negative, you get a circle. When the eccentricity is between 0 and 1, you get an ellipse. These are bound orbits. When the eccentricity is 1, you get a parabola. The total energy is exactly 0. And when the eccentricity is greater than 1, you get a hyperbola. And these two are unbound orbits. By the way, this is the calculation a similar calculation that Newton went through to prove that the elliptical paths of planets could be described by an inverse square law. So this is very similar calculation to Newton when he actually derived the physics equations. His laws of physics. Okay, so we're now going to look at the case of circular orbits and elliptical orbits in more detail. Here we're going to derive the stability of circular orbits to show that they're stable. We start by finding the equilibrium position. So finding the radius of a circular orbit. The simple way of doing this is to set the centripetal force equal to the inverse square law. We're going to do it a slightly different way. We're going to use the potential energy curve. So the circular orbit is going to be the equilibrium point at the bottom of this potential energy well. So we'll plug in the 1 over r dependence on the potential for an inverse square law. That's the centrifugal force. We find the equilibrium point by taking the gradient of the potential and setting it equal to 0. So when you take the derivative of it, you get k over r squared, and then this term has a 1 over r cubed dependence. Set that equal to 0 to find this point. Kind of cross multiply, simplify. It turns out that equilibrium position is the angular momentum squared over the k constant in the force times the reduced mass mu. Right, so that's going to be how far out or the distance between our masses for a circular orbit, given the angular momentum L. Okay, we're going to check for the stability of a circular orbit. We're going to show that it's stable. So to do that, we evaluate the curvature of the potential energy. Remember, if the potential energy has positive curvature, this thing is curving upwards. If it had negative curvature, it would be curving downwards. So we take the derivative of du dr. This is du dr. We calculated on the previous page. So we're going to take the derivative of that. We get this. So we'll plug in the equilibrium position R naught for R here and R here. We'll also plug in for K. So it turns out, because this is true, we can solve for K in terms of R naught. So K would be L squared over R naught mu. So we'll take this value and plug it in for K also. So there's the value for K, plugging in for R naught, we get this. And so we find that this second derivative is L squared over mu R naught to the fourth. Since mu is positive, L squared is positive, R to the fourth is positive. This is a positive number. It's greater than 0, so it's curving upward. And we have just shown that circular orbits are stable. We can calculate the orbital velocity, which will come in handy here in just a minute. So remember that the circular velocity is just going to be r times phi dot. And we can substitute the angular momentum of this. We can plug in, we can substitute this for the circular velocity. So the angular momentum is just mu circular velocity times r. So r naught, if we plug in the angular momentum in terms of the circular velocity, we get this. Simplify it, the mu, one of the mu's up top will cancel the one on the bottom. Solve for circular velocity, you get that. For the case of the gravitational force, mu is equal to this, k is equal to that. Plug in for k here, plug in for mu here. The m's cancel, the m1, m2's cancel, but big M is left over. And so it turns out the circular velocity is the square root of gm over the radius. You could derive this way more simply by just setting the centripetal force equaling to the gravitational force, set those two equal, and you get this immediately. But it's nice to see that this drops out of our potential energy approach also. So so this is the circular velocity. If we want to figure out the period, that is how long it takes the planet to go around the sun, well, the period is the circumference divided by the circular velocity. So period is 2 pi r over the velocity. Plug in for the circular velocity down the bottom, simplify, square both sides, and you can derive this result, that the period squared is related to the radial distance cubed. And this is actually a very similar equation is true for elliptical orbits, and this is called Newton's third law. Okay, so those are some results for circular orbits. We'll switch to elliptical orbits now. Elliptical orbits, remember, are for the eccentricities between 0 and 1. Here's our general equation for a conic section. And because these elliptical orbits were first demonstrated observationally for planets going around the sun by Kepler, these properties of elliptical orbits are called Kepler's laws historically. So there are 3 laws of planetary motion that Kepler described, and we're going to go through each of these separately. Kepler's first law simply says that planets go around the sun in ellipses. He demonstrated that observationally. We've just proven it based on Newton's laws, assuming an inverse square law. So you might remember that ellipses have two foci. Turns out one of those is at the position of the sun and the other one is equidistant on the other side. All ellipses are defined by, you can use the semi-major axis. So you take kind of the long axis through the ellipse, cut that in half. That's called the semi-major axis, from the center out to the long side. The total distance across would be 2a then. The semi-minor is the short side, or this diameter would be 2b. Turns out that the eccentricity, that parameter that we saw before, is 1 minus b squared over a squared. Sometimes the eccentricity is written as e, sometimes as epsilon. Sorry for mixing the notation, but it's the same as the epsilon term that we had before. Here are some examples of ellipses. So if an ellipse with an eccentricity of 0 is just a circle, an ellipse with an eccentricity of 0.9 is this really flattened thing. Just to kind of get you a feel for what these things look like. Turns out that most planets in our solar system have very small eccentricities, so they're very nearly circular. These are planets from Mercury out through Pluto and the other dwarf planets. So it turns out that a mathematical definition for an ellipse in polar coordinates is this. So it turns out that the thing on top is the semi-major axis times 1 minus the eccentricity squared divided by 1 plus e cosine theta. So that's the mathematical definition for an ellipse if you know the size of the ellipse. So remember, the distance from one side all the way to the other side is just 2a. So if you know that distance, this is the equation for it. When a planet is closest to the sun, that's called perihelion. That occurs when that angle theta or phi is equal to 0. So if you take the equation of the ellipse, you plug in 0 degrees, you get this term. You can factor this top thing into 1 minus e times 1 plus e. The 1 plus e's cancel, and you get that nice result. So it turns out that for an ellipse, the closest distance a planet can get, say, to the sun is just going to be the semi-major axis times 1 minus epsilon. The aphelion distance is going to be, well, I labeled this incorrectly, but it's the point over here. So the distance from the sun all the way over to the other side of the ellipse, that far distance, is the perihelion distance, and that happens when the angle is 180. Plug in cosine 180, that gives you a -1. So you get a 1 minus e. Factor this out, you get 1 minus e times 1 plus e. These 1 negative e's cancel, and you get this nice result that that should be P and A. That the aphelion distance, which again is the distance from here to there, that's the aphelion distance, is just the semi-major axis times 1 plus e. So here they're both labeled on there correctly. The aphelion point, the perihelion point. Turns out that if you think about things orbiting other objects, not like the sun, then you get different names. Astronomers have too much notation. So the perihelion point for this is the closest you can get to the sun. If you have a satellite or the moon orbiting the Earth, it's called perigee. If it's orbiting a star, you'd call it periastron. A galaxy, perigalacticon. If it's just some random object, you could call it the pericenter or the periapsis. Anyway, there's way too many terms for this. You can use this equation to derive what the angular momentum of the system is. So remember that Remember that this is the geometrical or mathematical definition of the ellipse. This is the equation we derive dynamically using Newton's laws, where c is equal to this value for gravitational force. So if we equate these two terms, we see that both of them have a 1 over eccentricity times cosine theta term, but the tops are different. So if both of these are describing the same ellipse, then this constant c, which is equal to this, must be equal to a times 1 minus e squared. So if you equate those two things, you get this. If you cross multiply by gm over gmu squared, and then solve for the angular momentum, you get this. So this is a way of writing what the angular momentum is in terms of the semi-major axis of the ellipse and the eccentricity and the masses. You can do a similar thing with the energy. If we start with the energy conservation equation like this, where that's the effective potential, since the energy is conserved, we can evaluate this at any point of the object in its orbit. So if we pick the perihelion point, like, right here, there's the sun, since it's at its closest point, the velocity vector has got to be perpendicular to the line connecting the planet to the object. That's got to be a right angle. So because of that, the object is neither moving towards the sun or going away from it. And so therefore, r dot is going to be 0. So this term is going to be 0. The radial kinetic energy term is 0. So that term goes away. The effective potential is just the total energy. We know that's the effective potential. So these two things combined give you that equation. If you plug in the perihelion distance and the angular momentum into that equation, you get this. You do a lot of simplifying. I'm going to let you go through this on your own to follow the steps. But it turns out that you get this nice simple result that the energy is just minus gmu over 2 times the semi-major axis A. So that's kind of a nice, elegant result. All right, let's look at Kepler's second law. Kepler's second law says that if you draw a line from the planet to the sun, that line will sweep out equal areas in equal amounts of time. So when the planet is far from the sun, it should move more slowly, so that this area is the same as this area right here. So assume that this is after the planet has moved 1 month. It's swept out this much area. Here, it's closer to the sun, so it's got to move farther, and so it's got to be moving more quickly. So here's an example of the object going around. You can see it tracing out those areas behind it. So Kepler's second law, saying that it sweeps out equal areas in equal times, it's going to turn out it's actually just a statement of conservation of angular momentum. So the area swept out in some time interval dt is going to be this. So you get that by constructing a little triangle here. So the length of the triangle is r. Approximately the height of this triangle is going to be r d theta. And so since the area of a triangle is 1/2 the length times the height, the area of that infinitesimal is going to be 1/2 r times r d theta. Kepler's second law claims that dA dt is going to be constant. So what we do is now we're going to take this and divide it by a dt. So we'll have a d phi dt here. So Kepler's second law claims that this thing is a constant. But remember that angular momentum is mu r squared phi dot. And we know that that's constant from conservation of angular momentum. So dA dt is 1/2 r squared phi dot. R squared phi dot is the angular momentum over the reduced mass mu. So r squared phi dot is just L over mu. So this just says that dA dt is equal to the angular momentum over 2 mu. And since the angular momentum is a constant, dA dt must be a constant. So basically we've shown that because angular momentum is conserved, dA dt must be a constant. And so Newton's second law follows directly from conservation of angular momentum. Okay, Kepler's third law. This is the final thing that we're going to talk about with ellipses. Kepler's third law says that the square of the period is proportional to the semi-major axis cubed. We've already seen that this is true for a circular orbit, because for a circular orbit, the radius is just the semi-major axis. But we want to prove this in general for ellipses. So we're going to start with Kepler's second law, that dA dt is the angular momentum over 2 mu. Consider consider one complete orbit. So if you imagine a planet going around an ellipse and then coming back to where it started from, the time for it to do that is, by definition, one period. The area swept out would just be the area of the ellipse. And it turns out that this is just a result from geometry, that the area of an ellipse is pi times the semi-major axis times the semi-minor axis, pi AB. So we can write this derivative as pi AB over the period as an average of the derivative over one entire orbit. We know that dA dt is just the angular momentum over 2 mu. So this thing in the middle must equal L over 2 mu. We don't like this b, so let's get rid of the b. That's not a variable we're used to with celestial mechanics. So we're going to use this expression that the eccentricity squared is 1 minus b squared over a squared. Solve for b, plug it in. We get that. We can now square both sides and then solve for the period to be this. And we can now plug in for the angular momentum. We know from the 2 slides ago, we know that this is the angular momentum. So we'll plug in for L squared. So taking this expression for the angular momentum, plugging in for L squared, some stuff cancels, some more stuff cancels, and we get the result that we were looking for, that the period squared is equal to 4 pi squared over g times the total mass of the system times the semi-major axis squared. Okay, so that's it. That was a lot of derivations, but hopefully this will give you an idea of how to work with the orbit equations to derive different results and do the homework.